we left with example. Steam enters an adiabatic diffuser, saturated vapor at 110 Celsius with a velocity of 220 meters per second. At the exit, pressure and temperature are 1.5 bar and 120 degrees Celsius, respectively. The exit area is 50 centimeters square, determined. Exit velocity, meter per second, and the mass flow rate in kilogram per second. Okay. We have steam flowing in and exiting. You can call this 1 and 2. Okay. So this is where we left. Not this. It's a saturated vapor. The inlet and exit, we know pressure and temperature. Okay. So we can find our properties at the inlet. Pressure, the inlet, or 1 will be 1.43 bar, right? Enthalpy, 2,691.5 kilojoules per kilogram. And specific volume at the inlet, 1.21 meter cube per kilogram. The exit enthalpy is 2,711.4 kilojoules per kilogram. Specific volume is 1.188 meter cube per kilogram. Okay. And I also know my velocity, the inlet, 220 meters per second. Okay. From first law of thermodynamics, after eliminating the terms we can neglect for this particular problem, right? We have left with velocity squared equals velocity at the inlet squared minus 2 enthalpy difference. Right? I know my enthalpy, the exit, the inlet, I know my velocity. Inlet, I can find my velocity. From here velocity, the exit square will be 220 meters per second square minus 2 H2. Enthalpy at the exit 2,711.4 kilojoules per kilogram minus 2,691.5 kilojoules per kilogram. Right? Times thousand meters squared per second squared 1 kilojoule per kilogram. I need a unit conversion to make these units equal. So V2 from here is 92.7 meter per second. And this is A. E, mass flow rate will be velocity, the exit, area at the exit divided by specific volume. Just on my velocity, 92.7 meters per second. Area, 50 centimeters square, 1 meter, 100 centimeters. Unit conversion. And specific volume is 1.188 meter cube per kilogram. Mass flow rate will be 0.39 kilogram per second. Any questions?
So when you're beginning values for like the specific volume, you got that from like the tables.
Tables. Okay. For now, we covered nozzles and diffusers, and we will go to another device, open system device, that we can amplify on first of all thermodynamics, right? Which is turbines. Okay? Continue on applications of the first law for open systems. Everything we had for nozzles and diffusers, first law of thermodynamics, and one inlet, one outlet steady state equations are valid here. Okay, we will be using those again. For steady state, let's remember what they were. Steady state Q, the inlet, plus mass flow rate at the inlet, summation of mass flow rate at the inlet times enthalpy plus kinetic energy plus potential energy, right, equals shaft plus the summation mass the exit or outlet, H out plus kinetic energy out plus potential energy out. Okay? And for one inlet, one outlet, for one inlet, one outlet, Q minus work shaft, enthalpy difference plus potential energy difference, kinetic energy difference plus potential energy difference. Now, we apply these equations, first of all, thermodynamics, on nozzles and diffusers. Now, our new topic is turbines. Turbines are also called work-producing devices. Okay? Work-producing means work is plus. Right? If you are given a turbine problem and your work is at the end of your solution is minus, you did something wrong. You should be plus. Okay? It's the work output plus. Okay? And the one inlet, one outlet. Again, it doesn't have to be with one inlet, one outlet. It might have multiple inlets and multiple outlets. And two, and the shaft work out. Okay. And for this particular schematic of turbine, we can apply one inlet, one outlet for a steady state system. Work shaft equals enthalpy difference plus kinetic energy difference plus potential energy difference. What turbine does is we have a high energy content substance entering turbine. Okay? What turbine does, expand the fluid. Right? It has blades inside, hundreds of them. That high energy content fluid heats those blades, turns those blades, produce work, and you take the less energy content fluid out. Right? You may understand better if we do so example. Example. Before we move on. So this, right? Usually turbines are designed adiabatically, okay? But it doesn't mean that in real applications, Q is zero. You have a leak somewhere. So Q is not absolutely zero, but that's the purpose. As an engineer, we want Q to be zero, as small as possible, right? So it's reasonable to accept Q is zero or negligible. Okay? And potential energy is typically zero. The elevation difference between exit and inlet considerably small compared to work is produced the device, turbine in this case. Okay, and kinetic energy difference is or negligible, typically negligible. Okay. So what we have left is work shaft equals minus delta H. Again, after neglecting these terms. Not always. Okay. All right. Example. Here enters a turbine at 6 bar, 740 Kelvin, and 120 meter per second. The exit conditions are 1 bar, 450 Kelvin, and 220 meters per second. A heat loss of 15 kilojoules per kilogram. Occurs, and the inlet area is 4.91 centimeter square. You're asked to determine A, the kinetic energy change in kilojoules per kilogram, B, the power output in kilowatts, and C, the ratio of the inlet to outlet pipe diameters. Okay. This is a good example to see kinetic energy and heat losses are not always negligible. Right? In this problem, we are given heat loss, which is 15 kilojoules per kilogram. It's not much, but we have to include it because it's given in the problem. And also kinetic energy difference. We have the velocity at the inlet. Even if it's 0 at the outlet, we have to include it. Okay? One inlet, one outlet. We have air used in the system. Okay. Goes through my boundaries, circulates in the system, and gets out to produce work. So pressure at the inlet is pressure 6 bar. Temperature is 740 Kelvin. Velocity is 120 meters per second. Area is 4.91 centimeters squared. The outlet pressure is 1 bar. Temperature is 450 Kelvin. And velocity is 220 meters per second. And we have also heat coming out, minus 15 kilojoules per kilogram. Okay. If you go to table A22, that's an air table, ideal gas air table. Based on a temperature, you can find your enthalpy, right, at the inlet and at the outlet. H1 will be 756.4 kilojoules per kilogram, and H2 will be 451.8 kilojoules per kilogram. For one inlet, one outlet, right? Mass flow rate at the inlet equals mass flow rate at the outlet, and 1 equals M2. 1, A1, A1, B2, A2 specific volume 2. And I also know from first law of thermodynamics, for one inlet, one outlet at a steady state system, Q minus work shaft equals enthalpy difference, kinetic energy difference, plus potential energy difference. All right. Okay. Here, potential energy is 0, it's negligible. Okay. A kinetic energy difference from state 1 to state 2, or from inlet 1 to exit 2, will be velocity 2 square minus velocity 1 square divided by 2, 220 meters per second square minus 120 meters per second, right, divided by 2. Right? And we need the unit conversion, 1,000 meters squared over second squared. From here, kinetic energy difference from 1 to 2, or inlet 1 to exit 2, inlet to an exit, will be 17 kilojoules per kilogram. Q minus work shaft from first law of thermodynamics, right? This had potential energy is negligible at 0. And work shaft will be Q minus enthalpy difference plus kinetic energy difference. Workshop will be Q is given minus 15 kilojoules per kilogram minus H1. We read it from table, is 700. H2 is 451.8 kilojoules per kilogram minus H1, 756.4 kilojoules per kilogram. And we have also kinetic energy minus 17 kilojoules per kilogram. Work shaft will be 272.6 kilojoules per kilogram. As you can see, heat loss and kinetic energy difference are minority compared to what we have, what we produce. Okay? And this is small turbine. And this is specific work. When we include the mass, the big difference will increase. Okay. Specific volume, we calculated R T1 over P1. Right? For air, R is 0.287 kilojoules per kilogram Kelvin times temperature is 740 Kelvin. For pressure is 6 100 kilopascal. From here, specific volume at the inlet will be 0.35 per meter cubed per kilogram. Now I can calculate my mass flow rate. I know area, I know velocity, and I know my specific volume. Here, mass flow rate will be velocity at the inlet is 120 meters per second. Area 4.91 centimeters squared times 1 meter equals 100 centimeter square over specific volume 0.354 meter cubed per kilogram. Mass flow rate will be 1.0.166 kilogram per second. Now I can find the total work produced in the turbine. Work shaft equals mass flow rate times work shaft equals 0.166 kilogram per second times 272.6 kilojoules per kilogram. We have 45 kilowatts. As work shaft. This is a work out. Or power out. Any questions so far? Okay. Part C, we're asked to find the ratio in diameters at the inlet and at the outlet. So I know my mass flow rate has to be equal, right, at the inlet and at the outlet. So I also know this is my mass flow rate at the inlet, mass flow rate at the outlet. Okay. Area, if I leave the areas out, right, ratio would be V2 over V1 times specific volume 1 over specific volume 2. And I also know T1 V1 over T1 will be equal to P2 H over T2. From here, V1 over V2, specific volume 1, the inlet over specific volume, the exit will be equal to P2 over P1 times T1 over T2. My area ratio, A1 over A2, will be equal to velocity at the exit divided by the velocity at the inlet times pressure at the outlet over pressure at the inlet times temperature at the inlet over temperature at the outlet. Okay, because I found the ratio between the specific volumes, and I put okay. I should have all of these to find the ratio between the areas. So A1 over A2 will be equal to velocity at the exit is 220 meters per second. Velocity at the inlet is 120 meters per second. Pressure at the outlet is 1 bar. Pressure at the inlet, 6 bar. Temperature is 740 Kelvin over 450 Kelvin. Should give us 0.5. But in the problem, asking the ratio of the inlet to the outlet pipe diameters. So I need to find the diameter ratio. D1 over D2 will be square root of A1 over A2 equal to 0.71. Okay, any questions? We just did a little trick here using ideal gas law and how to find our mass flow rate and combine them all. Okay. Let's get another example. A small gas turbine operating on hydrogen delivers 28 kilowatts. The gas enters the steady flow device, at 75 meters per second. through a cross-sectional area of 0.002 meters square. The inlet state is 240 kilopascal and 500 Kelvin. The outlet state is 100 kilopascal and 380 Kelvin. The exit area is 0.0016 meters squared. Determine A outlet velocity, the outlet velocity in meter per second, and B heat transfer rate in kilojoules per minute. Have a turbine, one inlet, one outlet. One inlet, one outlet. Using hydrogen as a substance. Hydrogen to produce work. And the work is 28 kilowatts. And we have also heat coming in. So we are asked to find that. The inlet pressure is 240 kilopascal. Temperature is 500 Kelvin. Velocity 75 meters per second. Area is 0.002 meters square. The exit pressure 100 kilopascal. Temperature 380 Kelvin. And exit area is 0.0016 meters square. Okay, let's remember first law for steady state, since it is stated in the problem, it's a steady device. Okay? M times mass flow rate times enthalpy difference plus potential energy difference plus kinetic energy difference. And choose CP at 450 Kelvin. But our heat average is 440 Kelvin. So if you choose at 450 Kelvin, or you can interpolate it, right? Linear interpolation, you will get pretty close. You can double check, but I will use 450 Kelvin. 450 Kelvin, CP at 450 Kelvin is 14.501 kilojoules, kilogram, degree Kelvin. Remember enthalpy, the constant specific heat model, right? Because we're not asked to solve in a variable specific heat model. If we are not asked to solve or use variable specific heat model, we can use constant specific heat model. Okay. CP is T2. Enthalpy difference is CP times temperature difference. Okay. CP is from table 14.501 kilojoules per kilogram Kelvin. And temperature T2 is 380 minus 500 Kelvin. Enthalpy difference here will be minus 1,740 kilojoules per kilogram. The inlet, specific volume at the inlet, or T1 over P1, or 8.314 kilojoules kilomole Kelvin divided by molecular weight of hydrogen is 2.018 kilogram per kilomole, right? Times the temperature is 500 Kelvin and pressure, the inlet is 240 kilopascal. It gives us 8.58 meter cubed per kilogram. Mass flow rate, the velocity, the inlet is given, the area, the inlet is given, and specific volume of the inlet. Velocity is 75 meters per second, area 0.002 meters square, over specific volume is 8.58 meters cubed per kilogram. Will give us 17.5 times minus 10 to the minus 3 kilograms per second. Specific volume at the outlet, 8.314 kilojoules kilomole Kelvin divided by 2.018 kilogram per kilomole. Temperature is 380 Kelvin divided by pressure at the exit is 100 kilopascal equals 15.66 meter cubed per kilogram. Knowing my mass flow rate, area at the exit, specific volume at the exit, I can find my velocity at the exit now. Velocity at the exit will be equal to mass flow rate times specific volume divided by the area. The mass flow rate is 17.5 times 10 to the minus 3 kilogram per second times 15.66 meter cube per kilogram divided by area 0.00616 meters squared. Give us velocity as 171 meters per second. Now, I can find my kinetic energy difference between inlet and outlet. Kinetic energy difference will be V2 square minus V1 square divided by 2. V2 is 171 meters per square minus 75 meters per second square divided by 2. I need a unit conversion to find kilojoules per kilogram. 1 kilojoules per kilogram. 1 kilojoules will be 1,000 meters square per second square. Kinetic energy difference will be 11.8 kilojoules per kilogram. Workshop. I know it's given in the problem. We are asked 28 kilowatts. We're asked to produce 28 kilowatts. And like 28 kilowatts in kilojoules will be 1 kilojoule, 1 kilowatt times second, right? So it will be 28 kilojoules per second. Q, heat entering the system will be equal to work shaft, okay, from first law of thermodynamics plus mass flow rate times enthalpy difference plus kinetic energy difference plus potential energy difference. Q, work is 28 kilojoules per second. Mass flow rate is 17.5 times 10 to the minus 3 kilogram per second. Enthalpy difference was minus 1,740 joules per kilogram plus 11 kilojoules per kilogram. Potential energy difference is negligible. Q from here minus 2.24 kilojoules per second, and we are asked to find the rate for kilojoules per minute. So multiply by 61 minute, which will give us minus 134.6 kilojoules per minute. Okay. Questions? Okay. I found a minus Q, but I showed plus Q. In this case, my arrow was wrong. Okay. So it will be Q out. Okay. I didn't know what it will be when I started this problem. And I picked one way, either in or out. I picked in, but my result gave me otherwise. Okay. So I go back and change it. Okay. Any questions? Okay. For now, we will stop solving problems on turbines unless you want more. If you don't, we will continue on compressors, pumps, and other open system devices. Okay. With the remaining time we have. 15 minutes will be enough. Okay. Or even 10 minutes. Okay. Compressors. Pump and fan. Unlike turbine, these devices are work-consuming devices. In turbine, our purpose is to produce work output. But compressor pumps and fans are work-consuming devices, meaning that I need to put work in for these guys to function. Okay. The work in this case is negative. And this is the schematic of compressor. With one inlet, one outlet. And this is pump. One inlet, one outlet. Again, same rules, but what we covered for open system devices or overall general open system. First law of thermodynamics for open systems. Okay. In, out, masses a lot through my boundaries and a constant volume. Okay? With one inlet, one outlet at a steady state open system device, Q minus workshop, delta H plus kinetic energy, delta kinetic energy plus delta potential energy. Again, in these devices are also, they are intended to be adiabatic, zero or negligible, just like turbines. Doesn't mean that it's always zero, but that's the intention. Zero or negligible. Kinetic energy difference are typically zero or negligible, and potential energy is just zero or negligible. So what I have left with for pump, for compressor, work shaft equals minus delta H. And for pump, also work shaft equals minus delta H, but with a little bit of difference. With the substance they operate, the difference is between compressor and pump, they function with a different substances. Compressor operates with compressible fluids, and pump operates with incompressible fluids. Okay? Incompressible fluids means that specific volume doesn't change, meaning density doesn't change. Okay? Density doesn't change, I can take advantage of that to find my enthalpy difference. Like this. Specific volume times pressure, okay? Only for pumps, which operates with an incompressible fluid. Okay? And that's another class, that's another course. Example. Water cooled compressor changes the state of refrigerant 22 from a saturated vapor at 1 bar to a pressure of 8 bars. The fluid rate is 0.9 kilogram per minute, and the cooling water removes heat at a rate of 140 kilojoules per meter. The power input is 3 kilowatts. Determine the exit temperature. Compressor with one inlet, one outlet. Work input is 3 kilowatts. Operates with refrigerant 22. And it's cooled down, right? The rate of 140 kilojoules per minute. This is minute. And one inlet, one outlet. One inlet, one outlet. Flow rate is 0.9 kilogram per minute. Inlet pressure is 1 bar. And it's saturated vapor, correct? So where is it on a saturate on a PV diagram? Where is saturated vapor? On the right lane, right? On the right line, correct? On this side for you. Okay, so it's on the line, not outside, not inside, on the line. So when you indicate on your TV diagrams, SH diagrams, you put your point on line. If you're off, it's not saturated vapor or saturated liquid. Okay. Outlet pressure, P2, is 8 bar, and we're asked to calculate temperature in Celsius. R22, if you go to table A8, you can read our enthalpy at the inlet because I know my pressure and I know the state of it. It's saturated vapor, correct? So if you do that, H1 would be 232.77 kilojoules per kilogram from table. Okay. Kinetic energy and potential energies are negligible. Because they're not mentioned in the problem. So I will assume that's the ideal case where kinetic energy and potential energies are 0, right? Okay. So from first off thermodynamics, Q minus work, right? Work shaft will be equal to, in this case, M times enthalpy difference. So enthalpy difference will be heat transfer rate form minus power consumed in the system divided by mass flow rate. Right? Heat system is cooled down the rate of 140 kilojoules per minute, right? Minus -3 kilowatts. Amount of power is required this particular open system device to operate, -3 kilowatts. I need to convert this to kilojoules. 1 kilojoule per second will be kilowatt, right? What else I have? And I need to convert this to minute. This to minute. 60 seconds per minute. Divided by the mass flow rate, 0.9 kilogram per minute. Enthalpy difference will be 44.44 kilojoules per kilogram. H2 will be equal to H1 plus delta H, right? Because delta H equals H2 minus H1. I know my H1. H1 is what? 232.77 kilojoules per kilogram plus 44.44 kilojoules per kilogram. So H2 will be 277.21 kilojoules per kilogram. What was my pressure at the outlet? It's 8 bar, right? If you go to table, refrigerant 22 table, right? I know my exit enthalpy now. For this exit enthalpy, this should exceed your saturated vapor volume, enthalpy volume, which puts you in superheated region, okay? So in net table, go to 8 bar in superheated table, right? Enthalpy, look for this number. This should stand lay between two numbers in temperature wise or inner properties. Okay, so temperature it will be between 40 and 45. Temperature 40, and you need to interpolate to find the temperature, exit temperature. 277.21 minus 274.42 divided by 278.20 x minus 274.42. From here, T2 will be 43.60 degrees Celsius. Okay. If we show this on a PV diagram, pressure bar versus meter cube per kilogram. I start somewhere around here. It's a saturated vapor. Hmm? And go up to superheated region by following this actual line. This dashed line is an adiabatic case. Okay? This is actual adiabatic line. It's an actual process line. And the dashed line is an adiabatic. So this system is not adiabatic, meaning that I have losses, right? Less efficient. So I will be off that line. Okay? Any questions? This will be all for today. Have a great weekend. I will see you on Tuesday.